Until recently, Dr. Rudy Schild and his colleagues believed they pretty much had the universe figured out.
But then, startling new information revealed that the cosmos was very different than they had imagined. Let's travel together with Dr. Schild to the edges of the known universe.
This is Mindshift.
We're very happy to have Dr. Rudy Schild with us today. Rudy is a member of the Harvard-Smithsonian Center for Astrophysics in Cambridge, and he has published over 200 scientific reports in refereed journals, especially the very prestigious Astrophysics journal.
It's so great for you to be here, Rudy, because Trish and I are both so excited about the work that you're doing. And I'd like to start with asking you about gravitational lensing. I think it's safe to say that you'll be in the astrophysics history books for your work in that area for a long time to come. But could you tell us, what is gravitational lensing and how is it used?
We celebrate Einstein now, and he predicted that if you have a distant mass, then light approaching that mass will get bent a little bit by the mass itself. That's the important point of his general theory of relativity, and this was the confirmation that made the theory popular in 1919. And in an extreme case of this, which I'm personally interested in, you can have a circumstance where a very distant object passing in front of a more foreground object, like a galaxy, can actually create two images of that background object. In my case, the background object is a quasar.
Does gravitational lensing let you know where the object really is?
It's a little bit subtle here because you have to do a good deal more work, but let's say that the actual object is effectively behind the lensing mass. And so I've made quite a long study of one of these particular gravitational lenses because, you know, the thing is so far away. I'm talking about now both the lensing mass and the quasar itself. They are so far away that they actually have sampled almost all of space and time. The light that I'm observing today actually left the quasar half the age of the universe ago. So if the universe age is about 13 billion years, it left this object about 6.5 billion years ago. Wow. So it tells us all the information about the structure of space and time itself, plus any defects that there might be in space and time due to gravitational waves, microlensing, due to individual masses in the galaxy, due to cosmic strings. All of those things are now available to further study because of this trick of nature.
A couple of years ago, something happened in astrophysics that was so big it made the front page of the New York Times, it made the evening news, and it had to do with something you guys are calling the accelerating universe.
Oh, yes.
So what is that, and why was it so important that it made the headlines?
It was importantly unexpected. And you recall that it came from an analysis of supernova brightnesses. And what we've come to understand, or what we believe about this, is that the universe was created in an inflationary event, as we said, 13 billion years ago.
That's the Big Bang?
That would be the Big Bang. And since that time, it's been on coast, but in a kind of a decelerating coast because the mutual mass of everything causes it to want to decelerate. But the discovery that was so unexpected was that it seems to have entered a new inflation phase. And that was not only unexpected, but it seems so contrary to our entire physical theory.
This discovery showed that those assumptions were incorrect?
That's right. The shattered assumptions had to do with the coasting. It was assumed that in the coasting phase, the universe's expansion should be slowing down, and we pretend that we know about the mass of the universe, we know its mass density from various observations of matter in the universe. And so suddenly we discovered that, wait a minute, the numbers don't match.
When this happens, does it really throw astrophysicists such as yourself off base because everything has changed?
Oh, quite so. It's all we have to talk about, really.
Okay. And does this kind of a change give you a different take on what we think of as dark matter?
Well, let's say that we're pretty sure in astronomy that there is an invisible part of the universe that's made up of the stuff that we always knew there was, the protons and electrons and carbon atoms. That I'll call ordinary dark matter. And I've had something to say about what that probably is and why there is dark matter. But I first want to mention that some people think that there's another kind of dark matter. We call that non-baryonic or unusual or unexpected dark matter. I'm not so sure that that kind exists. So let me go back to the kind that I really like to talk about.
Okay, and is that the baryonic?
That's the baryonic,
okay.
or what I would call the ordinary dark matter, the electron stuff, protons, hydrogen atoms, the stuff that I'm made of. We'd known that there must be more matter because when we look at a spinning galaxy, we can see that, there's not enough matter in the lights of all the stars that we can observe to hold that spinning galaxy together. Why isn't it splitting apart? Well, we've had to conclude that there must be some kind of dark matter that holds it together, that binds the spinning object.
With gravity?
The mutual gravity of the stars is not sufficient. There must be gravity from some unseen component called the dark matter that does hold it together.
And it's ordinary matter, but it's called dark because we can't see it.
And the problem is that it must exist in the space between the stars, and with no stars to illuminate it and no light of its own.
Okay, and that's
what's there
why
to see?
But are there any pictures?
Well, some pictures have been made where unexpected objects have been seen against the bright nebular background in some of these so-called planetary nebulae. These are objects which are just the expanding shell around a dying star. And when you look in there, sometimes you can see this dark matter object silhouetting the bright background.
Do you see it like a crescent moon or like a star?
Yeah, what it looks like is a blob, and if you can know where the star is, you notice that the star is shining on it so that the side facing the star is bright, not real bright, but kind of bright. And then there's a kind of a dark tail of stuff that's streaming away from the star. So we can actually see all this structure. First, let's recall that I see two images of my distant quasar. And remember that I said that if there are any defects in the structure of space and time, we will see them. And here's how that works. I notice that when I see the light of the two objects, the object is flickering a little bit, and I see those flickers in the two objects. Well, that's flickering that's intrinsic to the source itself. In other words, the quasar is flickering. But I also noticed that in one of the images, there was a flickering that was not in the other image. How could that be? It can't be intrinsic to the quasar. It must be that it's one of these defects of space and time. And astronomers have long known that such cosmic strings might exist. Now, you relate them to things that were at what we call Planck scales or subatomic scales at the very beginning when they were formed. But of course, since that time, 6.5, now twice that, 13 billion years ago, the universe has expanded. And so these structures that are tied to space expanded with the space and time. And so today, they're seen to be quite large.
So that's kind of a shift, isn't it, that you're applying quantum to the macro world?
Yes, there are some people who like this idea and have been able to show that, in fact, the masses and the sizes of the object that we compute correspond to approximately what had been expected for the subatomic scale object blown up by the inflation event.
So there's kind of a unity in nature.
It's all fitting together to that extent.
Rudy, how would you define quasar?
A quasar is not so hard to understand. I think by now we all know pretty well what a black hole is. The black hole is this massive thing somewhere in space containing the mass of 10 billion stars. And it has such an intense gravitational field that if a light ray were to try to go away from it, it actually would literally curve around and fall back in. That's because the light ray, as predicted by Einstein, has to respond to this intense gravitational field. And this produces what's called an event horizon, which is a space of a certain diameter around the black hole, beyond which nothing can propagate outside of the black hole. And suppose you talk about a really big one, so big that it's as massive as an entire galaxy of stars, which of course is about 1 billion or even 10 billion stars. If you imagine dumping all of that mass into something about the size of the sun, then you have a quasar.
Oh my
And
gosh.
the gravitational field of such an object is so immense that it strongly and dramatically warps the structure of space and time around it.
Wow.
We found very surprisingly that the structure seems to mimic the structure that had been already computed if the object were magnetic. So not only a monster of mass having 1 billion or 10 billion masses of the sun in mass, but also rotating and containing a magnetic field. Now, my colleagues don't all agree with me about this.
Okay.
However, they have also not criticized these observations, they just haven't taken this into account yet.
But this sounds very different than, say, those of us who've read about it in Scientific American or watched, shows on television. There's more, that information more comes from people like Stephen Hawking, does it?
Yeah?
But you're putting out something that's
And that's why I'm
different than
excited
that.
about it.
Okay.
You see, the traditional view has been that because of this very intense magnetic field, that there is a total disconnect between our space-time in our universe and the space-time that's in the black hole. In fact, we're not really even sure what's the dimension inside that black hole. We really can't know. It may not be a 3, 4-dimensional universe. Maybe it's some other dimension. How would we know? Because there is a fundamental and profound disconnect in the standard picture.
I see. But between our universe and the black hole, is there some kind of zone, or do they butt up? Or?
Well, there is the problem in the traditional theory that there is a zone of discontinuity called an event horizon. And many people now consider that an event horizon is the defining aspect of a black hole, and therefore the kinds of things that I'm seeing as having magnetic field are technically not a black hole. I don't know if you want to be quite so sophisticated. We would call it technically a MECO or MACO object. And in this new kind of object, where there is in the old theory a disconnect, we have not a disconnect but some very exotic quantum electrodynamic process that transfers the magnetic field from the inside to the outside and therefore creates a kind of quantum effect at the border.
So again, we're seeing quantum appearing in the macro realm.
It comes up again and again, and I like it because it's the point at which you can say there is a possibility that something that's non-deterministic in our universe is affecting and influencing our lives and everything about our universe. In other words, quantum mechanics in a very fundamental way sets limits to how much we can ever know about the universe.
In the black hole theory that I'm familiar with, light and information in light goes into the black hole, gone, it's destroyed. In your model, something different seems to be going on. Is the information destroyed? Is it preserved? Does it go in? Can it come out?
I'm glad you asked that question because it is totally awesome what happens at this, not technically event horizon, but this place where there should be this disconnect. Because in the new model, the new idea based on observations with the magnetic fields, what happens is that information does not actually penetrate into the black hole itself. It actually stays within our universe for all time. And what happens to it is that it now shifts to a high redshift. What I mean by that is that instead of, say, a light beam being at a visible wavelength of 5,000 angstroms, when it goes into this special space, it redshifts to a factor of about 1 billion higher frequency, but stays there and never really leaves our space-time. That means that it's in principle recoverable if you can have non-locality the way Edgar Mitchell described.
I wonder if you could explain to me exactly what non-locality is.
We, of course, know that light cannot propagate in the universe faster than the speed of light. And yet, there's some indications now that quantum effects occur simultaneously in ways that can't be explained by limited velocity like the speed of light. And so people talk about the quantum effects or quantum holograms, that is, quantum information, being present in the universe and changing simultaneously, not limited by the speed of light. And this does suggest that there is some mechanism by which this information can propagate faster than the universe, faster than the speed of light, but since nobody likes to talk about faster than the speed of light propagation in our universe, we have the euphemism of quantum non-locality, which covers it.
We talk about black hole and we talk about black holes. Can you explain to me, is there a black hole in our universe, or are there many? And I know you're talking about this huge one. How does that work?
You don't have to look so far away. There are some in our own galaxy. There is one huge one at the center of our galaxy. We call it Sagittarius A. And we know that it's smaller than the one that I've been talking about. We can actually see stars orbiting around that black hole. And so we can actually measure its mass, and we know that it's a mere 10 million solar masses. Well, what about the Andromeda Galaxy? Does it have a black hole?
Right.
Yes. Okay. All the galaxies apparently have a black hole at their center. And now you have to ask yourself, especially with this observation of a cosmic string, well, is there some larger space-time continuum that we need to know about and study that in some way connects all of these black holes together? Because remember that the important point that Brian Greene always stressed about the cosmic strings was that they imply a higher dimensionality to our universe.
What did you mean that this information could be preserved for all time? I mean, information, I'm taking it that you mean information as patterns of energy. What do you mean preserved? How is it preserved, and what do you mean for all time?
Very, very profound, actually. So again, at this special space that you're referring us to, let's say that the most obvious thing, like a sound wave or a light wave, enters. Let's say, stick with a light wave. What would happen is that as it enters this space, as seen by our universe, seen by a local observer watching this event, it would just move slower and slower and slower, and we would see it become redder and redder and redder in color. But the effects really become very dramatic in the sense that it gets so red that it becomes a microwave, actually.
Really? How is it preserved?
Well, that means that there's some sense in which if you can scan this space using non-local energy searches, then you might be able to contact that information provided that this process can occur at faster than the speed of light, which is controversial, but nonetheless seems to be the direction we're moving now.
What's in the black hole that would send information back out?
What indeed? Insofar as I'm free to totally speculate, now that cosmic strings are on the table, perhaps observed, we have on the table the idea that maybe there is some higher level of dimensionality in the universe that connects the interiors of the black holes. Maybe there's a network of black holes that are some information network, some consciousness, some working of the universe, some force directing processes in the universe, you name it, all that's on the table at this point.
Is it something like the galaxies are analogous to neurons in the brain, and somehow they're connected, and that information is shared, and that the whole cosmos is the mind?
Well, I like that. Now, I can't say that that's proved, but I can see it as a possibility. And those people who like to think that there is some higher intelligence guiding the universe, then you could imagine that source operates through these black holes at the point of these event horizons. Remember that I said that where the magnetic field is transferred from inside to outside, there has to be a great deal of this quantum electrodynamic chaos. And so that sets important limits on how much information we can ever know about processes occurring inside that black hole. Quantum chaos therefore provides a kind of boundary by which inside the black hole might be influencing things in our universe, but we couldn't really know that. All we would see is things are happening in our universe, and we would say they're probably random, but what if there is some guiding principle behind it all?
Like chaos theory, where it's chaotic, but there's really a larger order.
Very much so. And in fact, chaos theory almost certainly is going to play into this, but I have not gone that far yet because we're still arguing about the issue of, do we have good observational evidence for these magnetic fields?
What about the question of intelligent life on all these planets that you say are around the stars and in this universe with all these processes of which we know so little? Do you think the question of intelligent life will scientifically be understood in a very different way 10 or 15 years from now?
I would agree with the short answer, very certainly. It's important to understand that we now have seen planets orbiting stars in about 300 cases. And where it is so many, it takes an incredible act of faith to believe that life would have only originated on our Earth. Because look at it this way. We understand increasingly today that the process by which our solar system formed probably produced a great many more solar systems. And when we today see a star with a planet around it, we think that that's just the beginning. That star probably has a whole solar system of planets. And even though we can't really measure them all yet for technical reasons, you know, detectors get better, instruments get better, telescopes get bigger, and almost certainly we will come to the conclusion that all of these planetary systems exist with numerous planets. And now let's come back to our solar system. I mean, starting with the Sun, the first planet, Mercury, is too hot. The second planet, Venus, is also too hot. Probably no water, maybe vapor. Earth is just right. Mars is too cold now, but may have had a denser atmosphere in the past and probably had water in its past. And then Jupiter, Saturn, and the rest are probably too cold. But our solar system is probably typical. A few inner ones too hot, one just right, outer ones too cold. It seems likely.
Are you
Yes.
saying that every star that we see in the sky is probably got a solar system? Every star that we look at in the sky?
I would say probably yes. And if you want to modify that to, well, maybe only 1 in 10, does it really matter? When you go out and look at the night sky, do you know how many stars you see?
No, I don't.
There are 7,000 that you see just going to a dark sky site, but that's just the ones that you can easily see. And then if you look throughout the galaxy, it's 10 billion. So you have to conclude that almost certainly life has emerged on other planets.
Well, that would be a lovely place to pick up from the next time you come.
We hope that you enjoyed it as much as we did.
It is stimulating to talk about the new limits of knowledge.
So thank you very much, Rudy. This was exciting, and we're so glad you joined us today. I'm Trish Corbett.
I'm Michael Mannion. This is Mindshift.